Hello viewers, in today's session we are going to discuss one important problem from homogeneous differential equations of the type where we have to make the substitution y is equal to vx, where v is a function of x, right? So here we are going to solve this differential equation which is or which belongs to this type of homogeneous differential equations where we have to make use of the substitution y is equal to vx. So we have to solve 2xy dy over dx minus x square minus 3y square is equal to 0 when the conditions are x is equal to 1 and y is equal to 1, right? So here we'll find out the general solution of this differential equation, and then using this condition we'll find out the particular solution of this given differential equation, right? So let us start. So let us first rearrange the terms. That is, we can write 2xy dy over dx is equal to x square plus 3y square. So taking these two terms to the right hand side, and then we can write dy over dx is equal to x square plus 3y square divided by 2xy, right? So now here we see that the right hand side is a function of x and y, say f of x comma y, and here we have the derivative of y, that is dy over dx. So let us write this function like this. In the numerator we have x square plus 3y square. So the degree of each term in the numerator is 2. Here we have 2, here we have 2, and in the denominator the degree is again 1. So here we have 1 and here we have 1. So 1 plus 1 is 2, right? So let us take x square common in the numerator. So we have x square, then we can write 3 y square over x square, and in the denominator we have 2xy, right? Now here what we can do, we can cancel this x with this one, and we have x and 1 plus 3y square over x square, and here we have 2y, right? Now taking this x to the denominator of 2y, we can now write this expression as 1 plus 3 times y over x square, and then we can write 2 times y over x, right? So now we have converted this function f of x comma y like this, and this is a function, say f of y over x, right? And here we can see that this function f of capital F of y over x is a homogeneous function, right? Because we have expressed this function, that is f of x comma y, as f of y over x, and here we can write x raised to 0, because x raised to 0 is 1, and a function f of x comma y is said to be a homogeneous function if we can express f of x comma y as x raised to say n, and here we have f of y over x. So in this case this small f of x comma y is expressed like this, because here we have 1, right? So for 1 we can write x raised to 0. So if we compare these two expressions, then we can see that n is equal to 0, right? So the degree of this function f of x comma y, which is a homogeneous function, is 0. So the degree of this function is 0. So now, once we have established that this function is a homogeneous function of degree 0 and it is of this form, let us make this substitution, that is y is equal to vx, right? V times x. Or we can also write y over x is equal to v, right? So here v is a function of x, so let us differentiate both sides. So we have dy over dx is equal to dy dx of vx, and here applying the product rule, we have v times the derivative of x, and then we have x times the derivative of v. So here the derivative of x with respect to x is 1, so we have v times 1 plus x dv over dx, right? So we have dy over dx is equal to v plus x dv over dx. So let us make this substitution, that is dy over dx is equal to v plus x times dv over dx, and y is equal to vx in this equation. So now we have here dy over dx, and this expression is equal to this one. So we have 1 plus 3 times y over x square, and in the denominator we have 2 times y over x. So dy over dx is v plus x dv over dx, and here we have 1 plus uh, 3 v square, y over x is v, and in the denominator we have 2 times v, right? So the purpose of making this substitution, y is equal to vx and dy over dx as v plus x times dv over dx, is to reduce this differential equation into a variable separable form, right? So making these substitution, we can separate the variables, and then we can integrate, right? So let us take v to the right hand side. We have x dv over dx is equal to 1 plus 3v square over 2v minus v, and then we have 1 plus 3v square minus 2v times v is 2v square, and here we have 2v. So here we have 1 plus v square, so 3v square minus 2v square is v square, and here we have 2v. So now we can see that this is a function of v, and here we have x dv over dx. So let us separate the variables. So we can now write x dv is equal to 1 plus v square over 2v, and here we can write dx. So let us take a 2v to this side, and then 1 plus v square to the denominator, and here we have dv, and taking x to the denominator of dx, so we have dx over x. So now in the left hand side we have the variable v, and in the right hand side we have the variable x. So now this is a variable separable form of differential equation. So let us now integrate both sides. So now we can integrate both sides. So we have integral 2v over 1 plus v square dv, and here we have integral dx over x, and here we can write c as the constant of integration. Now here we can see that the derivative of 1 plus v square, it exists in the numerator. So here we can use an important and direct result from integration, that is, if we have the integrand of this form, that is, we have in the denominator say f of x, and its derivative exists in the numerator, that is f prime of x, then this integral is simply equal to log of f of x, right? And here we can see that the derivative of 1 plus v square is 2v, and it exists in the numerator. So the integral of 2v over 1 plus v square is natural log of 1 plus v square due to this result. And here the integral of 1 over x is simply a log of x, and here we have the constant of integration. So now let us take this natural log of x to the left hand side. We have natural log of 1 plus v square minus natural log of x, and here we have c. Now applying the properties of log, we have log of 1 plus v square over x, and here we have c. And here we have used this result, that is the natural log of m minus natural log of n is equal to natural log of m over n, right? So now here natural log of 1 plus v square over x is equal to c. So removing this natural log, we can now write 1 plus v square over x is equal to e raised to c, and e raised to c is again a constant. So let us replace e raised to c by some other constant, say k, right? So we can here write k. So now we have 1 plus v square is equal to kx, multiplying this k with this x, and replacing this v by y over x, we have 1 plus y square over x square is equal to kx. Now solving this, we have x square plus y square over x square is equal to kx, and we can now write x square plus y square is equal to x square times kx, that is kx cube, where k is some constant. So viewers, the general solution of this differential equation is given by x square plus y square is equal to kx cube. So this is our general solution containing this arbitrary constant k, right? So let us now find out the particular solution of this differential equation by utilizing this condition, that is when x is 1, y is equal to 1. So let us substitute x is equal to 1 and y is equal to 1 in this equation to get the value of this arbitrary constant k. So we have 1 square plus 1 square is equal to k times 1 cube. So we have now 1 plus 1 is equal to k times 1, that is 2 is equal to k. Now substituting k is equal to 2 in this equation, we have the particular solution as x square plus y square is equal to 2x cube, right? So viewers, this is how, by making this substitution y is equal to vx, we can easily find out the general solution of these kind of homogeneous differential equations.